Chapter 5 Reducing Airframe Noise NASA's major ERA goals included reducing and mitigating aircraft noise in communities adjacent to airports, a quest rendered more significant still because analysts predicted an average growth in U.S. carrier passenger flights of 2.2% per year between 2013 and 2033, with slightly higher than average growth in the first 5 years. An increase in takeoff and landing cycles could be expected to trigger an increase in noise complaints in communities surrounding affected airports. For decades, well over a half-century, reducing and mitigating aircraft noise had been a NASA, and NACA before it, area of interest. Traditionally, the greatest source of aircraft noise has been propulsion systems, particularly as the growl of piston and propeller systems gave way to the roar of turbojets. Over the past 50 years, air traffic increased dramatically and communities rapidly encroached on airport boundaries. Noise complaints soon became the number one issue reported to FAA public liaison offices around the country. Solutions ranging from restricting the number of flights allowed per day to nighttime curfews for commercial air carriers had an adverse economic impact. Noise abatement approaches and departure trajectories have mitigated the problem to some degree, but the most significant improvement was the advent of quieter turbofan engines. Advances in quiet engine technologies have resulted in such significant reductions in engine noise during takeoff and landing operations that, for current state-of-the-art aircraft, engine and airframe noise are nearly comparable. NASA researchers, therefore, sought to decrease airframe noise in order to minimize community exposure to aircraft acoustics. Primary sources of airframe noise include the wing high lift system, slats and flaps, and the undercarriage, nose and main landing gear. Secondary sources include slat brackets, flap actuators, and gaps between airframe and control surfaces. One According to Mehdi Karami, lead project investigator at LARC and ERA noise reduction element lead, a complete understanding of the problem requires full consideration of both engine noise and airframe noise contributions to an airplane's acoustic signature. You have to look at the problem from a system level, he said, because if you can reduce overall noise by 3 or 4 decibels, you have effectively cut it in half. ERA goals for N+2 civil transports called for a reduction of 32 decibels below current FAA Stage 4 standards, and a reduction of -42 decibels for aircraft entering service in the N+3 timeframe. Our dream is to see Stage 4 -71 decibels, said Karami, because by then you have essentially confined aircraft noise to within airport boundaries. To begin making these goals a reality, ERA managers established the flap edge and landing gear noise reduction ITD. Objectives for this effort included development of advanced modeling tools and capabilities that would enable aerodynamic and acoustic design considerations to be integrated concurrently early in the airframe design process, and innovations in effective noise reduction concepts. One such concept consisted of modifications to the side edges, tips, of the flaps to mitigate noise source regions by altering local steady and fluctuating flow fields. For landing gear, the addition of aerodynamic fairings altered the flow fields impinging on various gear components in a way that minimized pressure fluctuations on the gear surfaces. 3 During approach and landing, when engines are throttled back to reduce thrust, the noise generated by various parts of the airframe may be louder than that produced by the propulsion system. In order to effectively mitigate this problem, it is necessary to lessen the combined acoustic signatures from all major contributors concurrently. As you reduce noise from one source, Karami explained, another one becomes more prominent. The task is especially complicated because aircraft of different sizes and configurations offer different challenges. Any protuberance in an area where it creates turbulent flows will generate airframe noise, Karami said. Turbulent vortex filaments interacting with the flaps and landing gear merge together and become strong gear, creating pressure fluctuations on the aircraft's surface that we hear as noise. Initially, Karami led studies of the acoustic effects of specific structures such as the nose gear and flaps. I was working with Faye Collier under the subsonic fixed-wing program, and we made some measurements with a G550 aircraft in 2006, he recalled. Researchers at LARC then conducted further investigations with a small-scale, semi-span model of a G550 to look at several aircraft components and try to understand their effect on airframe noise characteristics. In 2009, the team decided to expand the research from just looking at individual components to visualizing the entire airplane as an integrated system. When the ERA project was created, we fully migrated our research to ERA because it was a technology development project, Karami said, and we wanted to develop new technologies to reduce airframe noise. He added that, during Phase 1 of ERA, our major focus was trying to see how much data we could get from scale models, and with the same G550 testbed we used in 2006, and in Phase 2 we made a full-blown effort to push our computational models. 5. The first step toward designing viable noise reduction technologies was to accelerate the development of high-fidelity simulation tools with accurate predictive capabilities. To this end, NASA partnered with Gulfstream Aviation for a comprehensive computational effort designed to advance the state-of-the-art in airframe noise prediction from scale models to system-level, full-size aircraft configurations. First, we simulated airflow over a semi-span scale model of a G550 in landing configuration to accurately capture the prominent noise sources at both flap tips for the baseline configuration, Kurami said. We then evaluated the effectiveness of noise reduction technologies applied to the flap tips. 6. Advanced computing software was key to success. Researchers used both the NASA LA-RC Fun 3D Unstructured Navier-Stokes Flow Solver and EXA Corporation's PowerFlow Lattice Boltzmann Flow Solver to perform time-accurate simulations. As efforts continued, the subscale half-span model was replaced with a full-span, full-scale baseline aircraft in landing configuration, with wing flaps deflected 39 degrees and the main landing gear deployed. Once again, simulated airflow over the model's virtual surface revealed the primary airframe noise sources associated with the G550. Kurami explained, "We focused our efforts on accurately resolving the local flow fields at 3 locations: the flap tips, the regions near the main landing gear, and the interaction zones between these two areas." 7. High-fidelity simulations enabled researchers to probe into the underlying noise-generating mechanisms associated with airflow over the flaps and landing gear, and to develop potential solutions. Because these simulations presented numerous challenges due to geometric complexities and requirements for a wide range of spatial and temporal resolution, all computations had to be performed on Pleiades, one of the world's most powerful supercomputers. This vital resource was located at ARC, where the NASA Advanced Supercomputing Division's visualization team created renderings from the resulting datasets. According to Kurami, even medium-resolution simulations required as many as 4,000 processors and 1.5 million processor hours and generated 40 to 50 terabytes of data. The knowledge gained from these computations allowed us to develop and improve several concepts that reduce the noise generated by these components, he said. 8. Wind tunnel tests set up several methods for mitigating airframe noise. Underwent aeroacoustic testing in the NASA LA-RC 14 by 22-foot subsonic wind tunnel during 3 test series, each lasting 4 to 5 weeks. The test article was an all-metal 18% scale, semi-span, high-fidelity model of a Gulfstream G550 aircraft. It was designed, fabricated, instrumented, and integrated at NASA LA-RC based on a set of airframe geometry files provided by Gulfstream. Model details included a 185.4-inch long half-span fuselage, a wing measuring 104.5 inches from the tunnel floor to the tip, a flow-through engine nacelle, engine pylon, and high-fidelity scale replicas of the flap and main landing gear. 9. The initial test series, completed in November 2010, documented the model's basic aerodynamic characteristics. At this time, researchers acquired measurements of such global forces as lift and drag, along with steady and unsteady surface pressure measurements. The second series of tests took place in February and March 2013. These experiments were dedicated to conducting comprehensive aeroacoustic testing of the model in a landing configuration, with and without flap/gear noise reduction devices installed. The third and final test series was completed in April 2013. These tests were devoted to collecting off-surface flow measurements from the model in baseline landing configuration with emphasis on gear-flap flow interactions. 10. Acquisition of acoustic measurements and determination of flyover sound directivity patterns for flap/gear noise sources necessitated that the wind tunnel facility be operated in an open wall mode in which the ceiling and the sidewalls of the tunnel test section were raised. This had been determined during the 2010 series, when tests demonstrated that the model's overall aerodynamic characteristics were largely unaffected regardless of whether the measurements were conducted with the test section in a closed wall or open wall mode. In order to reduce the adverse impact of background noise and improve the quality of the collected acoustic data, the tunnel had to be modified to operate 8 in a semi-anechoic acoustic mode. In this configuration, the test section floor, raised ceiling, and control room blast wall were all treated with sound-absorbing foam wedges, and the sidewalls were covered with perforated mesh skins backed by foam. Even the floor area outside of the test section was covered with soft foam slabs to absorb sound. 11 Acoustic measurements were obtained using a traversing microphone array constructed specifically for use in the LA-RC wind tunnel. The phased array consisted of 97 individual Growl and Care, B&K, Model 4938 quarter-inch pressure field microphones that were flush-mounted within an 8-foot diameter flat fiberglass honeycomb plate. An operational frequency range of approximately 1.5 to 80 kHz was achieved by placing the microphones in an irregular, circular pattern comprised of 16 arms with 6 microphones in each, and a single microphone positioned at the center of the array. The array panel, positioned at a lateral distance of 17.5 feet from the tunnel center line, was mounted on a rigid frame attached to 2 sets of 44-foot-long linear traversing rails. These rails were positioned in such a way as to allow the array to face the pressure side of the G550 model and permit smooth movement of the array panel in the streamwise direction along the full length of the test section. An additional set of 6 microphones was positioned around the phased array panel for use in characterization of noise directivity for various model configurations. Given that airframe noise during landing operations was a primary interest, a 39-degree flap setting with the main landing gear alternately installed and removed were the most heavily tested configurations. 12 Flap noise mitigation. In 2013, the research team experimented with several types of flap modifications to reduce noise. Because the model flap had been designed in a modular fashion, with removable inboard and outboard tips, it was possible to evaluate more than 30 permutations of 5 different design concepts. These included a porous skin treatment, a variety of bulk and locally reactive acoustic liners, flap edge noise reduction fins, Fenerfins, with both circular and non-circular cross-sections, flexible side edge link, Flexel, and reactive orthotropic lattice diffuser, ROLD. For all concepts tested, the extent of the tip area receiving treatment was carefully tailored to remain very small relative to the total flap surface area, and the spanwise extent of treated area scaled with local maximum flap thickness. To maintain the flap's overall aerodynamic efficiency, the first 10% of the flap cord at the leading edge remained unaltered. 13 The Poorest Tip Concept involved substituting the upper, lower, and side surfaces of the flap with a wire mesh skin having a specific acoustic resistance. Treated surfaces produced a cavity at each tip that allowed interaction between the external flow and the internal cavity fluid, air. Computational models and earlier studies guided the design of the porous surface treatment, which was tailored to minimize aerodynamic performance penalties while achieving substantial noise reduction. To achieve these goals, technicians fabricated cage-like structures at each tip to accommodate a wire mesh skin that was carefully spot welded to the cage to avoid creating surface imperfections. This resulted in a treated area that was continuous with the remaining flap surfaces. Researchers produced 4 sets of treated inboard and outboard tips with respective skin surface resistances of 150, 270, 450, and 570 rail, a unit of acoustic impedance. To determine whether the concept performed differently depending on the size of the treated area, they also tested an additional set of 270 rail tips where the spanwise extent of the treatment had been reduced by 33% on both upper and lower flap surfaces. 14 Researchers experimented with bulk and locally reactive acoustic liners, also applied to the flap tips. In one configuration, they fabricated a 6th set of porous tips with an extremely low resistive skin, 20 rail mesh, and then filled the interior volume of the cage with bulk absorbent materials. Tests were conducted using such fill materials as Nomex Felt Model 4485R and Face CR Alley, iron chromium aluminum yttrium, metal foam of varying densities. Experts at La RC also designed and tested a locally reactive acoustic liner that featured a series of serpentine channels of various lengths terminating within the inter-ryer volume adjacent to the flap tips. These channels were designed to achieve optimal absorption over a wide range of acoustic frequencies. Due to the small scale of the test model, it was impossible to obtain the most efficient design for maximizing sound absorption, but these tests served as useful proof of concept demonstrations. 15 Fenerfins are modifications consisting of an array of densely packed cone-like structures, fins, in a 3-dimensional arrangement extending inward in the spanwise direction from the flap side edge to reduce airframe noise generated by the interaction between unsteady airflow and the flap edge surface. Limiting control action to the steady and fluctuating fields within a very small region near the edges leaves the gross aerodynamic characteristics of the flap unaltered, minimizing aerodynamic penalties. The aeroacoustic environment created by the Fenerfins alters the effective boundary condition at the surface of the flap, significantly reducing the steady pressure differential experienced by the flap edge. As a result, the vortex formation process at the edge may be delayed or substantially weakened. 16 For subscale testing, the spanwise extent of the fin region, that is, the length of each Fenerfins element, followed a slanted pattern with the shortest fins applied near the leading edge and the longest toward the trailing edge of the flap. Researchers evaluated several Fenerfins concepts and discovered that circular cross-section fins with the smallest diameter tested produce the best noise reduction. 17 Researchers also experimented with a continuous mold line flap configuration. They conducted extensive testing of flexel, a structural link design in which the flap side edge is connected to the wing edge adjacent to the flap with stretchable hyperelastic materials. In order to effectively evaluate its noise reduction capability, the team tested both rigid polycarbonate and soft elastomeric versions of the flexel concept. An additional set of rigid flexel flap tips with a 40% larger transition section was fabricated to determine the effects of more extensive spanwise treatment on aerodynamic and acoustic performance. 18 The final flap modification, known as rolled, consisted of a honeycomb-like, interconnected structure added to the region of the flap that experiences the highest degree of sound-generating airflow instability. Rolled combined several attributes of the porous skin treatment and liner concepts. All three surfaces in the flap tip region were porous, and the internal structure was comprised of passages or perforations orthogonally aligned in all three directions. The intersection of passages from each direction created a three-dimensional lattice structure that was orthotropic in nature, that is, having elastic properties, in 2 or 3 planes perpendicular to each other. 19 researchers tested 3 sets of rolled flap tips with different sized holes, spaced evenly. Acoustic performance of the rolled concept improved as the size of the holes decreased, with the smallest diameters producing the highest noise reduction. 20 Each of the flap modifications tested could be easily retrofitted to existing aircraft structures, and several designs demonstrated significant noise reduction without adversely affecting aerodynamics. The porous characteristics of rolled and the gaps between Fenerfins fin elements changed the boundary condition at the surface of the flap, reducing the steady pressure differential experienced along the flap edge. This reduced turbulent flow and delayed the type of vortex formation that causes noise during landing approach. Aerodynamic penalties were minimized by limiting the control action to the steady and fluctuating fields within a very small region near the flap edge. Testing of the 18% scale model thoroughly validated earlier computational modeling. According to Mitigation, comparisons of fluctuating surface pressures between untreated and treated flaps showed an order of magnitude reduction of pressure fluctuation amplitude by 3 to 5 decibels. 21 Main landing gear noise mitigation. Mitigating noise from the main landing gear posed a greater challenge because an aircraft undercarriage comprises a complex system of subcomponents of various shapes and sizes. Whereas all flaps are generally similar in shape, landing gear configurations vary widely from aircraft to aircraft depending on size and mission requirements. Consequently, researchers realized, no single concept could be expected to produce the desired noise reduction levels. It quickly became apparent that they would have to approach the problem of gear noise reduction using multiple, complementary concepts tailored to specific noise sources associated with individual subcomponents. 22 Installation of aerodynamic and acoustically absorbent fairings over various gear components offered a relatively simple and effective solution. NASA researchers pursued initial design studies under a collaborative effort with industry partners Goodrich Landing Gear Services, EXA Corporation, and Gulfstream. During the subsequent developmental phase, Goodrich employed high-fidelity computer simulations to obtain a set of viable fairing concepts. Designers then used these same computational models to further refine the most promising concepts to achieve designs that provided at least the minimum desired noise reduction goals for each gear component. 23 To accurately evaluate the acoustic performance of the landing gear noise reduction concepts using the 18% scale model, technicians replaced the baseline Gulfstream landing gear with a modified set fabricated by Goodrich. Prior to installation, however, researchers placed the Goodrich gear into the Virginia Tech Stability Tunnel as a standalone test article. From September 2011 until July 2012, they tested the effectiveness of numerous permutations of 7 independent noise reduction concepts. The results guided researchers in identifying the most effective technologies to be further evaluated on the half-span model in the 14 by 22-foot wind tunnel at La RC in 2013.24. These technologies were simple but effective. First, technicians installed streamlined housings, collectively called upper fairings, over several existing components to mitigate turbulent flow fluctuations across the gear strut. A plug filled the void between the forward drag brace and the strut, and the landing gear door connecting rod was covered with an aerodynamic cover. Next, a more complex structure called a porous knee fairing covered the upstream main post, and a streamlined, tight-fitting fairing covered brake components located between the two wheels. Researchers were pleased to find that the knee fairing significantly diminished the noise-producing flow interaction between the front and rear struts. 25 An early brake fairing design performed well acoustically but was deemed impractical for application in a realistic environment at full scale due to brake cooling and maintenance issues. Instead, it was replaced with a larger aerodynamic fairing that partially covered the front portion of the two main wheels. Testing of both solid and partially porous wool fairings proved very effective in reducing aerodynamic noise, while avoiding the pitfalls of the earlier brake fairing concept. The only challenge left was to reduce the low-frequency noise associated with the wheel well cavity. The solution involved installing a stretchable mesh to cover the cavity opening. During tests on the isolated Goodrich gear in the Virginia Tech tunnel, mesh cover reduced low-frequency gear noise by more than 2 to 3 decibels. 26 researchers also strove to understand the complex phenomenology of noise produced by interactions between airflow and two or more closely aligned airframe components. The test model was representative of many types of aircraft in use today, wherein the deployed main landing gear is located underneath the wing and aligned with the inboard tip of the deflected flap. In this configuration, the turbulent wake of the main gear typically impinges on the flap edge at the inboard tip. The research campaign provided an excellent opportunity for a detailed examination of gear flap interactions in a realistic setting and their effects on the airplane's acoustic signature. Using various combinations of low-noise gear modifications and flap, researchers demonstrated that flap noise was largely unaffected by the deployed gear. The reduction in aerodynamic noise produced by the main landing gear was primarily attributed to a slowing of the flow impinging on the gear caused by flap downwash. As Karami noted, we showed that installation effects have a pronounced impact on gear noise, which was substantially reduced when the flap was deflected downward, as on landing approach. 27 Developing predictive tools testing new noise reduction technologies and hardware was only one aspect of the flap and landing gear noise reduction ITD. The other involved development of new design tools to aid engineers in modifying existing wing flaps and landing gear, or designing new ones, that would produce significantly reduced acoustic signatures during takeoff and landing. In the latter, ERA researchers pushed the state-of-the-art in airframe noise prediction modeling that could be applied to everything from subscale test articles to a full-scale aircraft with all its complex geometries. That was, I think, the most important thing to come out of our ITD, Karami said. By the end, we had developed a number of technologies that resulted in 4 or 5 patents, but I am most proud of the computational simulation. It was truly world-class. 28 The complexity of the problem created a serious challenge for engineers and programmers. Among the most daunting tasks was the development of a virtual full-scale geometry model from very old airframe design data provided by Gulfstream. These were data that had to be converted so we could use it in CAD, computer-aided design, models for both the wind tunnel and computer simulation, Karami explained, and that took a lot of detailed effort. But the resulting computational modeling software exceeded the team's wildest expectations. It was something most of us only dreamed of, he said, because we always thought it would happen perhaps 20 or 30 years from now. We put a lot of resources into it and a can-do mentality that we were going to push it until it couldn't be pushed anymore. 29 researchers compared preliminary computations to test results from the La RC wind tunnel, which had originally been built in the 1970s as an aerodynamic testing facility. It was later modified to allow aeroacoustic testing of rotary wing configurations and, under the auspices of the ERA project, underwent significant improvements to facilitate airframe noise testing of both conventional and unconventional aircraft configurations. In advance of tests with the G550 model, researchers measured tunnel background noise inside an empty test section, with and without airflow, employing an array of microphones positioned at specified flyover directivity angles that would later be used to acquire the model's acoustic signature. Additionally, a series of pyrotechnic charges was detonated along the center line of the empty tunnel in front of the microphone array to identify significant unwanted sound reflections that might cause spurious returns. With careful planning and extensive acoustic treatments applied to the test section floor, sidewalls, and ceiling, such interference was effectively eliminated. 30 There were, however, still obstacles to overcome. When acoustic engineers compared integrated sound pressure levels from the microphone array, computed over the entire measurement grid, with the spectrum obtained from the individual microphone mounted at the center of the array, they discoff-arid elevated tunnel background noise at both low and high frequencies. Jet shear layer interaction with the flow collector lip, which was not acoustically treated, seemed the most likely cause of the higher background noise at low frequencies. Elevated background noise at high frequencies was mostly due to roughness of the tunnel floor, which was formed from wire cages containing sound-absorbing foam wedges. This background noise rendered measurements with individual microphones unreliable for determining absolute noise levels for the model and had to be accounted for when processing the final test data. 31 Through direct comparison of computer-based models with wind tunnel test data and acoustic measurements obtained during the 2006 flight test, Karami's team successfully demonstrated that high-fidelity computer simulations could accurately predict the very complex fluid dynamic processes that generate airframe noise. It was like a puzzle, he said. We used all the pieces to shed some light on the problem, and to benchmark our computational tools. To find out how we were doing, we looked at how the computer modeling compared to the wind tunnel results and validated the results with flight testing. It was a step-by-step, or building block, approach. The ultimate goal was to develop technologies that could be applied to most current and future aircraft, but, more important, to have the ability to predict the noise both in terms of a baseline aircraft as well as for whatever future configurations emerged, and to see how much improvement had been made. 32. Modeling the acoustic signatures of flaps and slats was relatively easy because these aerodynamic devices have a high degree of universality. Whether installed on a regional jet, a 767, or something else, the basic configuration is very similar. Obviously, said Kurami, the noise prediction tools that we have developed can be applied regardless of aircraft geometry, whether it is a tube and wing or a hybrid wing body, and once you have the prediction tool, you can apply it to any concept, any configuration, and you can develop noise reduction technology for that particular configuration. 33. The problem of landing gear noise is much more complex because each type of aircraft has a different undercarriage geometry. Depending on the size and weight of the aircraft, the nose gear may have 1 or 2 wheels and the main gear may have as many as 3 on each gear truck. The more complex the gear arrangement, the more auxiliary components are necessary. All those little details can have an impact on how much noise is generated and how that noise propagates, Kurami explained. With a good prediction tool, you can see how the noise gets generated and figure out what other areas you have to go after, and then you can tailor your design as necessary. 34. Computational software for the project was adapted from an existing program developed by EXA Corporation for automotive applications. At the time that ERA began, EXA was seeking to expand the company's business from automotive to aerospace. It was a convergence of the right people at the right time, said Kurami. We also used some of our own in-house code as a benchmark to make sure their software worked for what we wanted to do. The EXA software proved well suited to highly complex geometries that challenged other codes. During our project, the EXA code was greatly expanded and improved because we pushed the state-of-the-art, he added. 35 Simulations performed for the ERA study constituted the first attempt to predict airframe noise radiating from a full-scale aircraft in landing configuration with most of the geometrical details included. NASA research results subsequently stimulated such aerospace industry giants as Boeing, Airbus, Gulfstream, Bombardier, Embraer, and others to consider applying these new predictive tools to current and future aircraft designs. Engine manufacturers also expressed interest. According to Kurami, our study will help NASA mature existing technologies and eventually produce new ones that will confine aircraft noise footprints within airport boundaries. 36 ERA planners originally intended to follow up modeling and wind tunnel testing with further flight tests of the G550 at NASA's Wallops Flight Facility, Virginia, to gather steady-state surface pressures on the wing and flaps, as well as unsteady pressures on the flap edges, nose, and main landing gear. To accomplish this, researchers developed a ground-based microphone array to measure the sound footprint of an airplane in flight. Dubbed an acoustic camera, it was designed to provide detailed information on the location and intensity of various noise sources as the airplane passed overhead. My only regret is that the flight tests for Phase 2 were not accomplished due to funding constraints at Gulfstream, Kurami lamented. We were going to fly in 2014, but after the critical design review something happened and the flights got cancelled. After that happened, NASA headquarters continued to express interest in conducting a full-scale demonstration at some point in the future. So in 2016, after ERA, we moved the array to Armstrong Flight Research Center, where NASA has a Gulfstream G3 testbed aircraft, said Kurami. It's quite a capable system, he added, so we are now trying to transfer the technology we developed under ERA to a flight demonstration at Armstrong. 37 This setback forced Kurami's research team to push the computational simulation to its fullest capability. Fortunately, the structure of the ERA project provided the necessary resources to do this. ERA was an unusual program because we knew exactly when it would start and when it would finish, he said. Headquarters was fully behind it throughout the 6-year span, and one of the reasons that ERA was so successful was that we had stable funding throughout. 38. Sound advice Stephen Rizzi, a senior researcher for aeroacoustics at LARC, led another team whose mission was to create technological tools capable of predicting and simulating sounds of flying machines still in the conceptual phase. Using computer models, flight measurements, and wind tunnel data, they developed methods for predicting the sonic characteristics that would be produced by aircraft of any given configuration. These data were then turned into a set of synthesized sounds that were played for people who volunteered to be subjects in what were dubbed psychoacoustic tests, measurements of how humans react to different levels of aircraft noise. Rizzi's system produced scientifically valid simulations of whirring rotors, roaring jet engines, and even the sounds of wind rushing over flaps and landing gear. Programmers had to consider such elements as distance, motion, the Doppler effect, and atmospheric influences on sound. 39 This process of studying a test subject's reaction, called oralization, is intended to help aircraft designers take noise into consideration when imagining new shapes and configurations. According to Rizzi, the automotive industry has been conducting similar tests for many years, but until recently there has not been a similar capability for aircraft designers. By putting these pieces of prediction and oralization together, he explained, we have created a new capability. 40 The new noise predicting software tool is called the NASA Oralization Framework, NAF. It incorporates a set of computer codes to transform noise predictions from numerical data into actual sounds. This is especially important if future aircraft are to be designed so as to cut noise to nearly 1/8 of what is currently allowed, and to confine the most annoying noise levels to within an airport's outer fence line. Until now, NASA researchers have relied on a number of older computer-based tools, including the ANOP, which was first developed during the mid-1970s. This program allowed acoustic engineers to calculate how much noise would be made by aircraft components such as engines, flaps, slats, landing gear, and any other protuberances sticking out into the slipstream and causing localized, noise-making turbulence. The advent of unconventional aircraft configurations such as the HWB necessitated development of a new, more versatile version called ANOP-2 to analyze noise produced by aircraft that don't follow the conventional tube and wing design. 41 By 2013, it was abundantly clear that numerical predictions alone were insufficient. The NAF, therefore, was developed by NASA and its partners as a complementary tool to ANOP. Rizzi explained that with the NAF, researchers input all the ANOP/ANOP-2 aircraft noise prediction calculations, process the information and, within minutes, produce an electronic audio file that can be played on any compatible sound system. The vision is that an engineer working on the aeroacoustics of a new airplane would be able to readily generate an oralization output in the form of a calibrated sound file, he said. 42 Having a realistic sound file available provides several major benefits. The first concerns how hearing the sound helps verify and validate the engineering processes used to make the prediction in the first place. If my prediction method is producing something that I know doesn't sound realistic, for example, if I am trying to oralize an aircraft already flying today to use as a reference and the file sounds nothing like the real thing, then that tells me something is wrong or missing in the process, Rizzi explained. 43 Sound files can also be used to evaluate how people respond to aircraft noise from various configurations. Using a concept called perception-influenced design, aircraft manufacturers can use these data to make an airplane quieter and less of an annoyance to communities surrounding affected airports. For example, a listener may hear two different sounds at the same decibel level but perceive them very differently. According to Rizzi, it doesn't matter how loud or quiet the sound is if it is perceived as annoying. With airplanes, two different engines may be equally loud in terms of decibels but may sound differently because of the way they are designed, making one more annoying than the other. As Rizzi noted, what we're trying to do is not only lower the decibel level to meet future noise regulations, but we also want to make sure that the resulting sound isn't objectionable to the public. 44 Rizzi believes the third major benefit is the capability to use sound files as a communication or public relations tool aimed at anyone who has a vested interest in how much noise an airplane makes near or at an airport. Interested parties include airport or airline officials, federal regulators, state and local lawmakers, and most especially members of the general public living in close proximity to an airport. With this tool we can share these sound files with the community so they can hear firsthand what a new jet engine or airplane design might sound like, said Rizzi. We can tell people we've made a reduction of 42 decibels in noise levels, but what does that sound like? How does that compare with current levels? Now we can demonstrate that with realistic sound. 45 In May 2016, during an international aeroacoustics conference in France, NASA used the NAF to demonstrate how several noise-reducing technologies evaluated during the ERA project would deliver on the promise of cutting noise to nearly 1/8 of today's standards. Prior to the conference, NASA researchers partnered with AMA Studios in London to combine the noise prediction sound files with flight simulator quality, computer-generated imagery representing two of the proposed future aircraft configurations studied for ERA. The result was a startlingly lifelike depiction that enabled designers to see as well as hear their work in action. Rizzi noted that the combined audiovisual presentation could also serve as a valuable tool to showcase to the public the dramatic reductions in perceived noise levels achieved by new aircraft designs. 46 In the initial set of videos, the two different aircraft were shown from the perspective of someone standing near a runway as the airplane was taking off, as well as near the end of the runway directly under the final approach path of the airplanes. One aircraft represented a typical twin-engine tube and wing configuration similar to a wide-body Boeing 777. The second aircraft was an HWB configuration with twin engines mounted on top of the airplane near the tail. If you watch the videos and compare the sound of the two aircraft, both in terms of the overall decibel level and the annoyance factor, there's no debate that the hybrid wing body represents a huge reduction in perceived noise, Rizzi said, adding that the videos were well received by those attending the conference, with many, in the audience, noting how helpful it was to be able to compare the sounds of the two different aircraft shown. 47 Oralization studies have continuing at a steady pace since 2001, with support from a number of the agency's armed programs, including the Rotary Wing and Aeronautical Sciences projects of the Fundamental Aeronautics Program and NACA. Researchers at LARC recruit test subjects as often as 4 times per year and pay them a modest amount to listen to sound simulations and register their reactions. Subjects sit in a small, theater-like room outfitted with 27 speakers and 4 subwoofers and answer questions on an electronic tablet while listening to simulated aircraft sounds. We conduct a test, we analyze the data, and we report on it, Rizzi said. Research results will become increasingly valuable in years ahead due to predicted growth in commercial air traffic and the advent of new technologies such as drones for delivering consumer goods. We're in a leadership position on this, Rizzi noted, describing his team's forward-thinking acoustics research. There is no organization I know of that has the capabilities that we do, it's a one-stop shop for this type of work. 48 He noted that his team had come a long way from initially focusing on making recordings of aircraft and reproducing those sounds in a controlled lab setting for test subjects. That works well if the aircraft you're interested in is a real aircraft, he said, but we work for NASA, so we're more interested in the future and there are no recordings of paper planes. That led us down the path of having to synthesize the sound. Rizzi knows what he's talking about. He is a musician in his spare time and he sees a clear relationship between the science of noise and the art of melody. There's a lot of overlap in the techniques used to generate the musical kinds of sounds and those used with aircraft noise synthesis, he said. It's why he enjoys his work so much. It's new and there aren't a lot of other people doing it. 49 In the spring of 2016, Rizzi's team demonstrated a NOF simulation of a proposed open rotor engine for a group of engineers from General Electric. They were evidently excited to hear the sound of the latest power plant, even before it actually flew. They really started thinking, wow, what can we do to change the character of the sound and make it more acceptable? Rizzi said. When you get a reaction like that based on your work, that's a pretty gratifying experience. 50. National Full-Scale Aerodynamics Complex, NFAC, 40 by 80 foot test section with a Boeing HWB model. The size of the NASA personnel gives a sense of the immense size of this 70-year-old facility. NASA.